Hello and welcome to reaction stoichiometry. Reaction stoichiometry is the idea of thinking about what you need to put into a reaction in order to get out what you want. So I started with the example of a simple cookie recipe. I don't know if this is real, so don't go use it. But if we knew that we wanted to come out with 24 cookies, so a recipe is typically written to give us 12 cookie if we put in all of the ingredients listed. If we wanted to instead make 24 cookies, think about what we would do with each of these ingredients. It's pretty obvious that we would want twice as many cookies, so we would double every ingredient. So to make 24 cookies, the amount of flour that we would need is our 2.25 cups, times 2, so we would need 4.5 cups flour. If we wanted to make 24 cookies, we'd also be doubling our eggs. So instead of using just 2 eggs, we would use 4 eggs. If we wanted to make 42 cookies, so this is kind of an interesting question because if we look at what 42 cookies actually is, it's a little bit less than 24. But without doing a ton of math, probably the easiest thing to do is just make 24. So if we made 24, we would use 2 bags of chips. And we could mathematically figure this out a little bit more exactly. One thing that we could actually look at doing is how much, if we just really truly wanted to make 42, we could say, hey, 42 cookies is, 1.75 dozen. So we could actually say, okay, we use 1.75 bags of chocolate chips. If I have tons of flour, plenty of sugar, and a bunch of chocolate chips, but only 7 eggs, this is going to limit how many cookies I'm able to make. So if I only have 7 eggs, and I need 2 each time that I do this recipe, I'm only going to be able to do this recipe 3.5 times. So I can make 3.5 dozen. That's the idea of something called a limiting reagent. So our limiting reagent here is the fact that we don't have enough eggs to make as many cookies as we want. So we'll talk about that concept a little bit later on. So if we need to relate quantities in a chemical reaction and we take a balanced reaction such as this one, our relationships are actually based on the coefficients. So in this reaction, we're reacting 2 moles of H2 with 1 mole of O2 to get 2 moles of H2O. Now we can also look at the grams involved here. So we actually have 4.03176 grams of hydrogen if we have 2 moles of hydrogen. We have 88 grams of oxygen. And for water, sorry, I should have calculated these ahead of time. We have a total of 36.0304. Now what you'll notice that relates to the last unit. If we were to round these to make it a little bit easier, we're really looking at adding 4 grams plus 32 grams, and that would indeed give us 36 grams. So those mass problems that we looked at in the last unit kind of work with these as well. That was just a simpler way of looking at it. When we look at it in this unit, it's kind of a little trickier sometimes. So we can actually take a reaction and determine, based on what we have, what we're starting with, how much we should be able to produce. So if we want to determine how many moles of oxygen are required to make 2 moles of water. So we already have the idea of conversion factors between grams and moles. Luckily here we're able to actually just stick with moles. So what I can tell from the problem is I can make a relationship between moles of oxygen and moles of water. So anytime I react 1 mole of oxygen, I get out of it, or I receive from the reaction 2 moles of water. I could write this the other way as well. I could say, oh, to get 2 moles of water, I require 1 mole of O2. So again, where these numbers are coming from, there's an invisible one right here. and there's a 2 right here. So that's where those numbers come from, and I can flip-flop this as needed in the problem. So I'm trying to solve for moles of oxygen to make 2 moles of water. So what I have to do here that's a little bit different than what I've done before is I'm actually going to be specific here and write, oops, I don't think I'm adding sig figs, sorry. I'm going to start with 2 moles, and I'm going to indicate that this is of H2O, because I'm dealing with moles of 2 different things here. I'm dealing with moles of water and moles of O2. Now, because I have moles of H2O on the bottom, I'm going to choose this as my conversion factor, because I want my answer to come out in moles of O2. So, I'm going to choose that conversion factor, and I've got 1 mole of O2 over 2 moles of H2O. It's going to cancel out my moles of H2O. Obviously, it's a pretty simple problem. We should have 1 mole of O2 that we need. Now, this can be answered in a very straightforward fashion by simply looking at this reaction, but this problem is a nice one to just kind of get a feel for, the process that we're going to be looking at here. So what if instead I only wanted to make 1 mole of water? So many of you can look at this reaction pretty easily and say, oh, that's half the water we have written. But what I'm going to do instead is walk through the problem and say, okay, I want to know how many moles of oxygen are required to make 1 mole of water. So I'm going to start with 1 mole of H2O. I'm going to put moles of H2O on the bottom. So I grab this 2 from right here, 2 moles of H2O. I've got a 1 right here, relates to 1 mole of O2. Moles of H2O cancel, 1 divided by 2 gives me 0.5 moles. So now we're going to build grams into this. So if we want to know how many grams of hydrogen are required to produce 36 grams of water. So we actually are going to need some gram formula masses here. One of the ones that we're going to use is we are going to use our GFM of hydrogen, which is this, and we are going to use our GFM of water, which is this. Now, these are conversion factors that we're going to be using to get between grams and moles. We also need to be able to look at how the moles of each of these quantities relate to each other. So we're comparing hydrogen and water. So our conversion factor here is pretty simple, actually. We have 2 moles of H2 and 2 moles of H2O. And again, we can flip-flop that as we need to. So I'm going to start with my 36 grams of water. So we do want to get in the habit when we have these reaction problems of writing our substance with our, with our amounts. Now, in order to talk about how H2O relates to H2, I have to get into moles. So in order to do that, I'm going to use my GFM, 18.0158 grams gives me 1 mole of H2O. I know, it's a lot to write, but it helps us keep track of stuff. So my grams of H2O are going to go away. So now for my moles, I can use the factor that I wrote up here directly as it's written. I've got 2 moles of H2O and 2 moles of H2. Now, mathematically in this problem, that obviously doesn't mathematically affect your answer at all, but it is nice to get in this habit of making sure that we change from one substance to another, because it's not typical that those numbers would be the same. Then, if we have 1 mole of H2, that is a mass of 2.01588 grams. Oops, sorry. Keep wanting to not make 8s correctly. So you're going to go ahead and you're going to multiply across the top and divide by the bottom. We're able to keep 2 sig figs, so you should have about 4 grams. Now, in terms of thinking about if this makes sense, 36 grams of water is about 2 grams of water, or 2 moles of water. So you should expect to produce about 2 moles of water, and that should require about 2 moles of hydrogen, which is about 4 grams. So I know how many liters of hydrogen gas would be required to make 5 moles of water. So the reason I included this question is because it really allows you to see, hey, we can take any starting amount and we can work through the problem. So we're going to start with our 5 moles of water. And we need to relate this to hydrogen, which needs to be in liters, but one step at a time. So we go to our reaction first to relate water to hydrogen. So again, we're going to have our same molar relationship we had in the last problem, which is 2 moles of H2O relating to 2 moles of H2. Moles of H2O go away. Now, what makes this question a little bit different is we're not going to use any GFMs because we just want to put hydrogen into liters. And they're telling us it's a gas, so we can make that STP assumption in this question. If we have 1 mole of any gas, including H2, at STP, it will occupy 22.4 liters of space. We can keep that H2 with it for clarity. Moles go away. So we do 5 times 2 times 22.4. Divided by 2. So you should get 112 liters for sig figs. We do consider these to be exact numbers. So we're going to be able to keep 2 sig figs here. So this is 110 liters. So we can go ahead and pause the video for a minute, and I will put the answers to each of these up. So let's take a minute and look at these 2 problems. And the first one we started with our 72 grams of water. That's what the problem gave us. So just to be clear on where that came from. And we then have to convert that into moles of water. So in order to use the reaction to compare things, we have to go into moles. So we have the step where we take grams into moles. Then we're going to use this step right here. This is what allows us to compare our moles from our reaction. Now, some people have asked me before, because I have this 18 here, this is the mass of 1 mole right here. Why don't we multiply that by 2 if there's a 2 in front of this in the reaction? We are doing that in this step, but it is better to do this stepwise because in more complicated problems that can get a little bit confusing. So this 2-to-2 relationship is what allows us to convert from water into hydrogen using what's given to us in the reaction. Our last step there, and I'm sorry, I should have hydrogen with this, is our calculation of our number of grams of hydrogen. In our next one right here, we start with that conversion where we go grams of H2O into moles of H2O. This step right here, this allows us to go from moles of H2O to moles of O2 using my reaction. And then in my last step, I'm turning my moles of O2 into grams of O2. And with 3 sig figs, we get 47, we get 48.0. So I've gotten 47.957, so that's going to round with keeping my 3 sig figs. You can try this problem right here, and we'll go over it in just a moment. So we're going to start by taking our grams of water into moles of water. So 117 divided by 31.9988. Essentially, it's about 3.5 moles of water that we then have to convert into oxygen. We're doing this using the relationship of 2 waters to 1 oxygen. So that 2-to-1 relationship right there. And then we're going to do one more step where we take our moles of water, of oxygen, and we use that 22.4 relationship to turn that into our number of liters. And we are allowed to actually keep quite a few sig figs here. We're allowed to keep 3. So this is going to be, oh boy, this is a fun one, huh? So it was 40.95 to keep 3 sig figs. We would actually call this 41.0 liters. So we'll be doing the ammonia practice problems together tomorrow to get a little bit more working on this.